All right, so now that we've talked about the planar density and how we calculate planes, now we're going to look at the close packed planes. And as it may sound, this is the plane that has the highest possible planar density. We call it close packed because of that reason. And that, in fact, was the 111 plane in FCC that we just worked on in the previous example. So that number that you saw is the highest possible planar density that we could ever expect if we're dealing with two dimensions, so a plane, and equally sized circles or atoms. So that's the highest that we could expect. So this is the same one that you saw in that previous module. So what I want to look at now is the FCC structure as a whole. We can think of as how we can think of that structure being broken down into the stacking of various close-packed 111 planes. So what I'm going to show you now is basically a projection of that, a two-dimensional projection. So we're going to start with the two dimensions. You can see here the green atoms represent a close-packed plane that we just draw. So if you want to sort of verify that, you can draw that equilateral triangle and see that all these atoms are touching, right? And so that's the portion inside the unit cell. And then if you extend it, you get the form of this as the close packed plane. So this is the first plane, the first 111 plane. So then what we're going to do is we're going to look at the next plane, and we're going to look at it on top, and we're going to draw them in, but we're only going to draw them in with open circles. So this is the next plane. And this is, again, a close packed plane. It's a 111 type. It belongs to that family. And what we see is that the center of that circle, the center of that atom, basically is situated over an empty spot, right? One of those interstitial places. So this is where that B atom can kind of nestle down into the lowest spot, into this empty spot above. And so that's what we see with the next atom, or the next plane up. And that's the B, we call those the B sites, whereas the first one we called A sites. So now we're going to have one more plane above it that we're going to describe, and that's going to be, again, another close packed plane, but we're only going to show a few of the atoms for convenience here. And they also, again, go over the empty sites, but in this time they go over the empty sites in the B site, and they're also not directly aligned with the atoms in the A site. So they're basically an empty spot of both. You see that you can see the white going all the way through. So we call these the C sites because there are different positions than either the A or the B. So you can kind of see the progression A, B, C. So we're shifting each one of them slightly differently. And so if we look at a unit cell, we can visualize that as well. So the green ones in the back represent the A sites, then these blue ones represent the B sites, and then the one over here on this corner represents a C site. And this is the stacking. So we're basically stacking different 111 type planes, and that can give us the greater FCC structure. And so we can show it in a number of different ways. If we want to show larger amounts of the units of the structure, you can see that here and here. So this is just a way of representing the FCC structure with just stacking of the close packed plane. And so why do I care about that? Is because I want to compare it to a different one. So now if I look at that, so this is the 111 plane that we drew within the FCC unit cell. But let's say I draw a couple more, right? And now, if I look at this, and we want to look at what it looks like, if you kind of imagine this, if you ignore this top atom here and just focus on these, this looks like a hexagon, right? And sure enough, if you just focus on these, this is the same plane as what we see in that hexagonal close packed, right? And so this, you can see them here. So these atoms are the same as these over here. So the close packed plane that is 111 in FCC is also the close packed plane in the hexagonal close pack. But in this case, it's the top and the bottom planes, in which we call the basal plane. So those are the same, right? You can draw it in a slightly different way, but it's still a close packed arrangement. And so if we look at the HCP structure a little bit more, we can also identify the stacking of those. So here on the bottom, this bottom basal plane had that same arrangement, the close packed arrangement that we saw on the FCC 111. And so that's the A sites. So then the next plane up is actually the half plane. It's here in the middle. And these three atoms go into the empty spots between the A sites. And you see that represented here with the green as the A sites and the blue as the B sites. And so they sit over those interstitial, those kind of nestled into the empty spots. And then above it, you have the other basal plane on the top that corresponds to the positions of these sites below. So this has the same position as this, just elevated up. So this type of arrangement we call A, B, AB stacking, because we only have two different distinct sequences. Whereas in the FCC, if you go back to that one, there was three positions, A, B, C, A, B, C. So that's when we talk about the stacking sequences of these two materials. But the main thing to take away here is that FCC and HCP both are the close packed structures, three-dimensional structures, so they have an atomic packing factor of 0.74, and they also contain close packed planes. For FCC, that's the 111 we talked about, and here for HCP, it's the 0001 plane, which we also call the basal plane. And the only difference between the two is how we stack. FCC, we stacked ABC, ABC. With hexagonal, we stack AB, AB, AB. Those are the main differences between those two types. But I mentioned that there's a lot of connection between those two structures.